Our next speaker is Chris Jones, Director of Applications with Quantique. Chris's presentation topic, Securing Your RISC-V Design End-to-End Using Quantum-Driven Technology. Chris will detail how Quantique's quantum-driven unforgeable device ID in silicon QDID adds the highest level of security to Andes RISC-V CPU's internal security features for an Internet of Things chip design. Please welcome Chris Jones.
Thank you very much for Andes allowing us to speak today. Really appreciate it. And what I'm going to talk to you guys about is securing your RISC-V designs. I'm going to show you how technology at Quantique can provide you true end-to-end security for your customers' RISC-V designs. So a quick intro of Quantique. So we're based out in London. We've been around since 2016. And what we're trying to do is simplify security and make it much easier for customers making products with RISC-V cores to make and manufacture their products securely. It means they don't have to trust all the guys in the supply chain if they use our technology. So we have mature products. There's two product families we have. One is a hardware IP, and the other is a security platform, which basically manages the security of a device throughout its life cycle. Just wanted to note that Vijay mentioned us earlier. We have been chosen as the root of trust for end-to-end security for Intel's Pathfinder for both our QDID and Quantique. So I'll talk about those in a little bit more detail later on. So some of our partners, obviously part of the RISC-V community and Pathfinder, and we have partnerships with a lot of semiconductor guys out there because our technology is primarily targeted the IP at obviously semiconductor devices, MCUs, SoCs, ASICs, that kind of thing. So we have two families that we provide our customers. One is this hardware IP, which is basically part of a hardware root of trust. So this is based on a quantum effect, so that's why it's called the quantum-driven identity. And once integrated into a semiconductor device, it provides that device with a truly unique identity. It has very high entropy, and it's unforgeable, tamper-proof, and impossible to counterfeit because it's based on a quantum effect, so it's not unlike typical PUF technology, which I'll talk about soon. Main differences is it means that you don't have to inject keys into your design, which is a very costly process as part of the manufacturing process. And of course, you have to trust the folks that are injecting the keys for you. The device also creates multiple uncorrelated keys, which is unlike first-generation PUFs. And then we have our other family, which is the Quantique family, which is a software package which manages the security of the device throughout its life cycle. So it manages certificates, usages. It becomes the CA of your IoT infrastructure. So I'll talk about that later on. So hands up, who's heard of a PUF before? So a PUF is a physical unclonable function. They've been around a while. There are different types. Typically, the most popular are SRAM type and the Flash-based. These are first-generation PUFs. Here at Quantique, we have designed a second-generation PUF, a new type of PUF, which doesn't use other peripherals that are in the actual target device. It's actually designed from the ground up to be based on security and is a secure element. That's why we call it a second-generation PUF. Now, it's based on a quantum effect. We actually measure quantum tunneling currents in a transistor. And that gives us a very high entropy and our unforgeable capabilities. And what it does is it creates this unique identity in every single chip that the device is integrated in. Everyone is different, and it comes from very high entropy. So what does this mean? It means that we can manage simply the identity of the device throughout its life cycle. The security is based on that provable identity, which is based on this PUF device, and it means we can basically do this zero-touch capability throughout the life cycle of the device. Over there, you've got a diagram showing you the actual currents from a PUF that we actually measure. So we measure down to tens of picoamps of the quantum tunneling currents of the transistors in the array. And I'll talk about that a little bit more as we move on. So I just wanted to talk to you a little bit about first generation puffs. I mentioned these SRAM puffs and flash-based puffs. These were developed some time ago where it was seen that you could actually take peripherals that are currently available in microcontrollers such as SRAM and puff and flash, and you could use those to actually generate random numbers. Typically with SRAM, every time you power up an SRAM array, it actually comes up reasonably in the same kind of state every time, but there's some bits that are problematic, and you need some kind of error correction software to manage that. In the case of flash, you can actually injure the flash cells. So you could take two flash cells and injure them both, and based on the kind of the mismatch of the silicon between the two cells you're actually measuring, the difference in the dopants, you could get a 1 or a 0 from the cell. Again, kind of a random in nature. So these are peripherals that are currently in MCUs and ASICs, and they were used to generate puffs. Benefits of them. So cost of key injection was removed. You didn't need to inject keys into the device. The identities are not stored in memory, which is a big plus. So your identity is not actually stored in some kind of flash memory that you can easily access. It's simply stored, in the case of SRAM, when you power up the SRAM cells. And the SRAM and Flash is already available in the device. So this is really handy and useful to generate a puff from these peripherals that are already there. So it's quite an advantage there. And they're available in a lot of microcontrollers today. But what are the limitations of this first generation? Typically, the puffs could only generate one key, and you typically then had to run an algorithm to spawn other keys off that to generate multiple keys. The cells didn't always start up in the same preferred state as you'd expect, and in the case of SRAM cells, you can get up to 30% bit error rates from SRAM cells, which means you have to have a lot of software to actually run the error correction algorithm. So the software overhead is quite high. Reliability of the performance is dependent on special memory manufacturers. So different manufacturers of SRAM had different entropy values. And it was very questionable resistance against side channel attacks. You could do a lot of photon emission measurements on the SRAM, skim the back of the die, and actually measure the currents in the SRAM cells. And you could actually then get access to the fingerprints. It's not a self-contained IP. It's reliant on memory that's actually already in the device, and relatively long setup time. And in the case of flash, you tend to need a large pump to actually generate high voltage to corrupt the flash cell. Now in the QDID, this is the second generation device. You can see here over on the right, there's a picture of looks like a bunch of noisy pixels in an array. That basically represents our array. So we have an array of dual transistors, and what we do is we measure the tunneling current across each of those pairs of resistors, and from that, we measure a difference in those currents, and we get a fingerprint from the device. Now, with our second generation puff, you don't need to inject keys into your device to give it provable identity. So we're not talking about just a number in the device. You actually have to prove that you own that identity cryptographically. And now you can do that with our puff. You don't need to inject keys. Therefore, you don't need to have HSM on your production line. You don't need to trust anybody. And the cool thing about the seed that's generated by the QDID is that nobody ever knows what the private key is inside that device to represent its identity. You can't find it out. So that's a major part of the zero-touch technology that I'm talking about. Any of the identities are not stored in memory. They're actually stored effectively in the crystalline structure of that die. And we read the quantum tunneling currents out, so it's actually not possible to see anything physically in the device to represent the fingerprint. It works on standard CMOS transistors, FinFETs as well, so it's quite easy to implement. It is an analog IP, of course, but it is just based on standard CMOS transistors. It operates on technologies or line widths down under 90 nanometers. Above 90 nanometers, the quantum tunneling current is just so small that we can't detect it. The cool thing about it is it's got a very low error rate, so we don't need a lot of error correction software to support the device. multiple uncorrelated keys. That's unlike any of the first generation puffs. So you can get multiple keys which could be used for different applications. Typically, we use one of them to represent the identity, another to be used for downloading encrypted firmware onto a bare metal device. Again, that helps with not having to trust third parties when they're injecting your firmware while building your boards. And it's very high entropy because it's based on a quantum effect, of course. So we're actually using that to show its unforgeability. It's not possible to counterfeit it, and even with a medium-sized quantum computer, whatever that is, I guess, it's not going to be possible to determine what the fingerprint is of each array. So this is a second-generation puff that has been designed specifically to represent identity in a device. It's not making use of other peripherals. It is a security peripheral. So that's our hardware IP. Very easy to integrate into a device, black box. And this is supported by our security platform. So we call this the Quark Link. We like using Q a lot. And it doesn't mean we're affiliated with the James Bond franchise, but we do have cool tech just like the Q branch. So Quark Link, this is a software package. It's agnostic to where it runs. It runs in a Docker container. It can run in the cloud, on the customer's server. It doesn't really care, as long as its device that it's managing can actually connect to it. So at the bottom here, you see a circle which represents the device. So that's your RISC-V product. Now, typically, when that is going to be connected to the cloud, when it's being manufactured, it needs keys, cryptographic keys to be injected, certificates. They need to be registered with the cloud service. It's quite complex. In fact, it's very complex, and it's time-consuming and costly. With our system, you don't have to do that at the manufacturing site. So say you were making a intelligent fridge that had some cameras in it, photographed your food, and it sent the camera pictures up to an app in the cloud, and it sent you a recipe, something like that. When the fridge actually came off the production line and out the door, it doesn't have to have all those certificates and keys and all the registration inside the device during the manufacturing. So it reduces the cost. And you're not dealing with secure credentials that you're trying to inject into the part. You just need to have its identity, which comes from the QDID, and a certificate to allow it to authenticate against its Quark Link. So you just ship it out the door, and it doesn't know what it's going to connect to, apart from it just knows it's going to connect to a Quark Link. What happens is you configure your Quark Link. It's very easy. We're trying to make security really simple. Very simple GUI just says, for this device with this identity, connect it to this cloud service with this security credentials. Very easy to configure. And that's it. The system is ready. So the fridge goes out the door. The end customer buys it from the local store, takes it home, connects it to his network. The first thing the fridge does is contact its Quark Link because it has no idea what to connect to. Contacts the Quark Link, has a certificate inside. It's got capabilities to run TCP/IP in a TLS stack. It sets up a secure link with a Quark Link, and the Quark Link says, right, that's your identity. I'll attest it, authenticate it. Yep, you're the guy. I've been configured to send you this secure information to connect to your cloud. The Quark Link deals with all the PKI automatically. It is the CA. It is a CA for that IoT ecosystem. So it manages all that for you. And it also registers the device with the cloud service, all automatically. You don't have to deal with it. It sends all the information down to the device and disconnects. Now the device connects to the IoT hub, which you can see in here, which could be AWS or Azure or whoever. Connects to that securely. It's been registered, and it talks to its application. And this happens in milliseconds. You wouldn't know that it's actually contacted somebody else before it contacted the application to run your fridge. And this is where we provide the simplicity of connecting to the cloud, which is pretty complex. Oh, yes, there is a small client running in the device, but it is pretty small. The main amount of software in the device will be the TCP/IP link and the TLS. Our actual library is very small. And then the Quark Link then has created the PKI and the certificate, so it's managing that device now for the rest of its life. So it can issue certificates, revoke certificates, renew them, of course, and it can handle software downloads. Again, very simple to use. I'll be set up outside if you want to actually have a look at QuarkLink later on. I'll give you a quick demo of how it all operates. It does have a hardware security module in the background. We use a cloud-based one. But again, we keep that away from the customer, so the customer doesn't need to understand about certificates and keys and how they're managed. That's just handled by the QuarkLink for you. Very easy to use. So this is just showing that whole journey I described. So you start off with the IP, you put it into a semiconductor device. That gives your device a unique identity, which is cryptographically provable, which is important. That forms part of your root of trust. Goes into your SOC, and you can then extract the device identities of your devices that you're building. Then it moves on to, you can put it into a product. You need to inject some firmware, the customer's firmware. You can actually use another key in the QDID to encrypt that firmware and inject encrypted firmware into the bare metal as part of the encryption of the firmware. Then once the board is up and running, you can then authenticate using the QDID, send down the credentials to the device, enroll onto the QuarkLink, and then that then onboards the device to the cloud service, because the QuarkLink has sent all the secure information down to the device. So the unforgeable identity, the QDID, is really just the start of the journey. But once you have that in the product, it makes it so much easier to run through the rest of this complex journey and get that device connected to the cloud. So we really are simplifying that process. So we talk about this zero trust supply chain. Because you don't have to inject keys into the device, it means you don't have to trust anybody, and it's low cost. The device can't be counterfeited based on the quantum identity. Authentic encrypted firmware can be downloaded to the bare metal device. That's always a weak point. But you can encrypt it straight away, so you don't have to trust any board stuffers or board builders that are doing your product. And you're protecting that customer's software IP. The IoT security then throughout its lifetime means that we have built-in certificate authority, which is often quite costly, buying certificates from certificate CAs. You don't have to do that with the QuarkLink. It's doing that for you. We can reissue certificates at no cost. It's managing your PKI for you. So we do the enrollment and onboarding. We test any firmware that's running on the device, and we do all the certificate and key management transparently. And of course, we can do firmware over the air because we can manage those certificates as well. I've just got a boot process here just showing you that the QDID also has a public key integrated into that IP, which allows us to send down signed software that forms part of the first level bootloader secure boot of the target device, and allows us to extract things like the IDs out of the device. So there's a report that Intel released which talked about how much it costs to actually provision an IoT device. So if you say in a smart building, you're fitting sensors all around the building, it turns out that it's very expensive in engineering time to have that deployed and onboarded to a cloud service. And here we're just highlighting the different parts of that journey to actually connect an IoT device in such a system. So you need a root of trust, which we've talked about. QDID forms part of that. And then there's that provisioning step. We actually have to have some kind of software injected into the bare metal device to actually just get it up and running. So that's part of the zero trust supply chain, where we provide security to ensure that that is safe. Then that onboarding is this actual connection of the device to the cloud service. And then later, once it's running over many years, you need to manage the security of that device. So this report came out, and as I said, it was just an exercise that we did. And we actually looked at the different costs involved in each one of those steps. So putting a root of trust in was very small. Provisioning, so we're talking about actually having secure hardware in a secure program facility on the manufacturing line. But it's the onboarding, which I know that seems very high, but that's basically what the report came out with from Intel. That's the kind of cost of hiring field engineers and the time to actually connect devices and make sure they're connected correctly to a cloud service, and then a lifecycle management. So it's looking at the sort of cost savings that we here can provide customers when adding security to their system. Because they often look at security and think, you know, I'm not being forced yet to do it, the standards aren't out yet, I keep kicking the can down the road of adding security, but we can show that we can certainly reduce the cost of doing that today. And there we've got the integration costs of doing all that work, of getting a device connected to the cloud. It is difficult, it takes engineering time, takes expertise, so there is additional costs on top of that. But the savings that you have with the systems that we're presenting are certainly useful. So Andes Core with integrate. How does a QDID work with the Andes Core? So I have here a slide that actually shows you where it actually fits. So you take a RISC-V core, and typically what you'd have is a TE, or trusted execution environment, which would have your keys and manage the actual security of your device. And typically it's a separate element. It can be something that's hidden behind some kind of hardware firewall, but ideally it needs to be some kind of engine with cryptographic accelerators and capabilities within it. So here you can see we've got the root of trust. The QDID is a small part of that. That's actually being used to provide the identity. It needs to be closely coupled with an ECC core to generate keys from the seeds that are generated by the QDID. So there is some peripherals needed around it. But you have here this root of trust, and that's where you would have your certificate, your key generation, any signing, verification, etc., would be passed over from the core over to the TE through the interfaces, DMA, or typically some kind of mailbox system. So that's how the QDID forms part of a system in a device. Just some examples. So typically we see this type of text used in IoT gateways. So you have a kind of a concentrator of IT devices. May have Bluetooth, low RAN, all sorts of low data rate sensors and peripherals. And they're all aggregated in some kind of gateway. And typically you want to make sure that that gateway is secure. So this is just kind of an example use case. PLC, of course, is very famous. A few of those have been hacked with dire consequences. So it's often a good target for that kind of use case. And then it's just some typical smart city. We see a lot of uptake in this kind of technology. So in summary, between ourselves and Andes, we can provide the most complete and secure RISC-V solution for your end customers. So highly optimized processor cores, which you've seen today, pretty impressive stuff. Extensive software stacks available from Andes. And then the root of trust uses the QDID, that's our part in the deal, and the cloud-based security platform. So the actual cloud that manages that security throughout its lifecycle. And of course the professional IDs that come from Andes. And this will enable your customers not to have to kick that security can down the road any longer. And they can build products that are secure and high performance with RISC technology. They don't have to trust partners in the supply chain. It makes it so much easier for them to onboard their devices to cloud services and utilize the capability of cloud services that we've seen are out there. Improve their products. And they don't need to have experts in security on their teams. Using the QuarkLink is very easy, and we certainly can make sure that you don't need some kind of security guy to manage the security of the customer's IoT ecosystem. As I said, I'll have some demos running outside if you're interested in looking at the QuarkLink. Also visit our website, cryptoquantique.com. And that concludes my presentation, and thanks very much for listening.